Hey there, fellow wackadoos! Hello again, and welcome back to Dr. Doodle's QBasic Asylum. Oh man, what an episode we got this time. Oh, you're gonna love this. Actually wanted to save this one for episode 40 to start the next chapter off with a bang, but this one's just such a milestone, I couldn't wait. So if you look at the title up there somewhere, Playing God in QBasic, heaven help us. That's right, we're playing God, we're creating life. Well, we're not creating life, just simulating it here on the screen. And well, hang on, take a look here, I'll show what I mean. Alright, here we have our code up and running. Now this is an adaptation of a very famous computer simulation by a British mathematician by the name of John Conway, hence the name Conway's Game of Life, except my adaptation, as you can see, is called Life and Death. Because let's face it, if you're born, you're gonna die. And that's exactly what happens here. You got what we have here is a field of squares here, which in the game terminology, these are cells, like single-celled animals, paramecium, amoebas, bacterium, whatever. Now, here we see a bunch of dark blue cells. That means they're all dead. If I click here, we got that yellow cell. That's a live cell right there. Now, the rules of the game or the simulation are as such. Any cell with 0 or 1 live neighbors, the 8 cells surrounding it there, with 0 or 1 live neighbors, it's going to die of starvation, because these little guys are predators. Actually, nasty little cannibals. But to be fair, it's not like you can swing down to Mac Daddy's, grab an Egg McMuffin, right? So they eat what they got. And what do they got? Neighbors. And to be honest, I have a couple neighbors I wouldn't mind having over for dinner. But in any case, so this one here's got no neighbors, no live neighbors, so it's going to die of starvation. Now, if a live cell has 2 or 3 live neighbors, then it's cool. It's got something for dinner, maybe toss a neighbor in the freezer for breakfast tomorrow. We're all good. Now, 4 or more live neighbors, well, we're in trouble. I mean, I can fight off a couple predators, but 4 of them, no way. One of them's going to get you, you know. And so, sure enough, you got 4 or more live neighbors. They kill off this cell, and it's dead. But now here's the magic for the whole program. The last rule, if a dead cell has exactly 3 live neighbors, it comes back to, well, it doesn't come back to life. It's repopulated by one of those live neighbors. Because, you know, they eat him, they got plenty of chow, now they multiply, and the cell that was dead now becomes alive. So that's it. 0 to 1 live neighbors, cell is dead. 2 to 3 live neighbors, cell is, if it's alive, it stays alive, no problem. 4 or more live neighbors, it's dead for predation, really. I mean, I can't keep up with that many predators. So in any case, let's try this. We'll hit randomize here. And as you said, well, here's the pattern here. There's another. Now, this program, as I said, is famous. Now, tens of thousands of people around the world have adapted their own version of this game, this simulation. Entire computer sciences have sprung up around this game theory, chaos theory, and there are web pages dedicated to it. The Life Wiki. There's all kinds of videos on YouTube about the game of. Oh, look at this guy right here. See that? That's what's known as a spaceship, actually a glider. But yeah, so all these people have noticed these different patterns that just arrive out of nowhere. All right, now the Game of Life simulation is a deep topic, so it's going to be a long video, and as such, I've split it up into 2 pieces. They're both pieces are in this video, but I'll have a part 1 where we talk about the history of the game, how it works and all. And then part 2 is basically the program itself and the code. So just, if you want, skip to like chapter 2.1, chapter 2.2, etc. So just look at the chapters on the bottom and you can skip to the part you want to go to. Yeah, so hang on, here we go. Hold on a second, let me show you something. Now, being QBasic, this particular version is blisteringly slow. I mean, excruciatingly slow. But I'll show you something. This particular formation, this is known as a Herschel. We've got 3 horizontal, 3 down, and then 2 over here. That's known as a Herschel, named for the fellow who first noticed this or discovered it. So if we hit start here, boom, it now turns to pause, and as you can see, it's going. As I said, I'll speed this up as post-production here. But it seems to be doing just random nothing, and then all of a sudden, oh, look here. we got this, that little thing is a spaceship known as a glider, but I've written this program, so I am the creator, and I've decided his name is Adam, because he's the first we've seen, right? That's that little guy. He's just jogging along, inhale, exhale, doing this thing, just jogging along. Meanwhile, the Herschel up here, whatever it's doing, just some kind of mess, and who knows what's going on up there, but he's just jogging along, doing his thing. Oh, look here. Now, here's another glider. This is Eve over here. Now, I happen to know that Eve, she's on the warpath. She's gonna scalp Adam because he left the toilet seat up, you know, so she finds him, oh, he's doomed, you know. Well, let's see. Is she going to find? Here she comes, but Adam's hiding down here. And if you notice, Adam went down on the bottom, and now he comes from the top, now over this way. So this is what, 40 rows by 50 columns, so only 2,000 squares. But the edges wrap around, so it's kind of like a globe. Theoretically, it's an infinite globe, if you will. They can just keep going and going and going. So here comes Eve. Adam's coming her way. Will they meet up? Looks like Adam might be in trouble here. He's going to meet up with, this is called a still life. And is he going to be all right? Or, oh, there he goes. But looks, Eve hasn't got much longer to grieve for him because she's gone too. All right, so our simulation's gone stagnant. Now we do what's called a post-mortem here. Click. And down here we see this generation 211. So there are 211 cycles, or 211 generations, as the game calls it. Our population is 8. There's 4 in there, 4 there, and the status is stagnant. So we can click here to clear the field, and then we move over here and click with the left mouse button, and I can just draw any kind of random pattern I want or something. I'll show there's specific formations people have found, but now we click on start. And there we go. We start our simulation. Start is now the pause button. So we click again, we can pause. There we go. We pause what we got here. And in any case, so we got life and death up here. There's start and pause. Clear, as you can guess, clears the screen. Randomize, you saw that. The post-mortem, that gives them the little report on what's going on in our field here. Then there's the help button. And click here, you can see this shows examples of some of the formations talked about. Now, the most common are called still lifes, like this block. It just sits there, doesn't do anything. The block, the beehive, tub, boat. This is how to create these things. Aircraft, carrier, ship. Then we have oscillators, things that just flip back and forth. The blinker, for example. You might have seen a couple go vertical, horizontal, vertical, horizontal. There's the toad. That one's fun. I like that. The clock, the beacon, and then the decathlon. That was neat. It's got like 15, goes through 15 cycles before it finally looks like that again. Below this, we've got our spaceships. You saw the little glider going along. Now here's a lightweight spaceship. There's also medium and heavyweights. I didn't bother with those. But the glider gun, we'll get to those in a minute. But we'll clear this, and I'll show you again. Here are some of our still lifes. We got, let's see here, the block. We got the loaf. What's another one? Oh, yeah, the boat, or tub, I guess it is. Think that's it, like that. And then we got a couple of oscillators. There's that's the blinker. This is my favorite here. Oop, called the clock, right there. What else? We got the decathlon. We'll put that in here. Oh, I should probably do that lower because it expands a bit. Two cells, 4 cells, 2 cells, and then seal up the holes. What else is there? There's the toad. Got to show you the toad. I love the toad. So we start this now. Boom, and there we go. Our still life's up at top here doing nothing. Now I like to think of them as livestock because they don't do anything. But if something collides with it, it can throw everything all in a whack. There's the bar, the clock, the toad. Here's the decathlon doing its thing down here. So yeah, like as I say, tens of thousands of people have run this simulation. And I'm talking like on super duper computers with, instead of 40 by 50, we're tens of thousands of columns, tens of thousands or millions of these cells, right? And they got these things running for days on end, all kinds of weird patterns, just from those four simple rules that we had about how many neighbors you have, and all these things happen. So we'll clear here, click randomize again, and as you see, now, nearly every time that I click randomize, sooner or later we see a little glider go. Just 5 little cells that create that. There he is, right there. There's a glider. There's another one right there. Just randomly appear out of nowhere. But those, I'll show you. Hold on, clear here. We can draw a glider. They're pretty simple. Just like a zigzag with a little tail right there. And then there's also, this is, let's see, down 3 over 3. Yeah, and the tails there. This is what's known as the lightweight spaceship. If I start this, okay, now the glider, he's coming down diagonally. This lightweight spaceship here, it kind of looks like a little ducky there, right? There's a little duck, but it goes horizontal. And of course, this is all symmetrical, so this can be drawn backward, up or down, any direction. It just rolls through this and that. The gliders can go up, down, left, right. Now, we'll clear this and take a look at help screen again. If you notice this bottom one here, the glider gun, this whole configuration here is called a glider gun. And it's called that because it pumps out a constant stream of gliders. Hang on a second, I'll set that up. I'll probably speed this up because it's pretty slow, but hang on. Stick with me a minute. Alright, now here I've set up my glider gun down the bottom here. This little figuration here configured, that's called an eater. It just eats up the gliders, and you'll see what I'm talking about here. We'll start. It goes through, I don't know, a bunch of cycles or generations until eventually we'll see, yep, there's a glider right there. Now these two here are just bouncing back and forth. They're basically just oscillators, but they keep colliding with each other, creating, here comes, yeah, another glider there. And then another will come again. This is excruciatingly slow being QBasic, but on faster machines, faster languages, they blast out lightning fast. And here comes another one. But you can see we've got a steady stream of these gliders coming down here, and soon eventually they'll hit up with this eater, which just, as the name implies, eats the glider. And there we go, gone. The next will come out, it'll eat that one. What happens if we pause here, and now we get rid of this eater? I click on the left mouse to bring a cell to life, click the right one and it kills it. So let's get rid of this eater here. And now we restart. Start again. Glider's coming down. Now, as I said, it wraps around, so it's like an infinite globe, really. And there's, up the top, here it comes again. This time, he's going to collide with the glider gun, and that won't be so good. Not good for anybody. There we go. Eventually, this whole thing's going to go, well, is that thing going to die? Eventually, we'll speed it up. We'll see what happens. Here comes our last glider now, and as I've said, they're small, and they may nearly every time I randomize this program, I get one of these gliders. It may even last only just a couple of generations, but don't discount it because there's been numerous times I've run the simulation and it looks like everything's stagnant and dead. And here comes one stupid little glider and beeps up everything, messes it all up again, and I mean it can go on for generations. Looks like we still got something happening down here. Let's see what the glider's going to do. Yep, we're stagnant here, as I say. We got one oscillator here just blinking away. Everything else is a still life. But let's see what's going to happen with Adam here. He's been resurrected. Come on, brother. Alright, there we go. He's gone, and we're pretty much stagnant. So now we click the post-mortem button. We see we have 474 generations, population of 28, and the status is stagnant. Now the status report, I kind of cheated with that because there really is no way to tell. It's completely chaotic. You can't tell what's going to happen. But I figure out of 2,000 cells here, first of all, well, let's clear this, do a post-mortem. Our status is vacant. We've got nothing here. Now, if I click 1, again, post-mortem, population 1, it's called stagnant. I figure if you got less than, say, 200 live cells, well, you probably haven't clicked the post-mortem until it's gone stagnant. But if it hasn't already, it probably will go stagnant. Now, from 200 up to, say, 1,600 or so, that's what, 3/4. It's chaotic. It's going to evolve quite a while, but eventually should go stagnant. More than that, and that's called viral. It's just going to explode, continue exploding forever, as far as we know. So there's no way to really, I'm just kind of taking a guess here. If there's this many, if there's 0, it's vacant. 1 to 200, I call that stagnant. As you see, more than 200 up to, I think, 1,600, that's chaotic. Anything more than that is viral. Just a fun little function I put in there. So that's that. We'll clear this and hit quick, and we're done. So that's our code. And as I mentioned, people, the tens of thousands of programmers around the world have been working with us for decades. The game was actually invented in 1970, I believe it was, at Cambridge in England. And people have been studying, and they found the different formations. In fact, you just saw 2 of the gliders, or 2 of the spaceships, I should say. But there are hundreds of them. As I mentioned, I think it's called the Life Wiki, or what is it? Well, of course, Wikipedia's got a page on the game of life, and YouTube's got dozens of videos. I forgot to mention, and one of the spaceships that I saw just recently is called the Puffer Breeder. It's a huge spaceship, hundreds of cells, and it's called the Puffer because it kind of looks like an overblown puffer fish. And it's called the Breeder because everywhere it goes, it poops out glider guns. That's right, the spaceship just glides along, pooping out glider guns, and here come the gliders. And I don't know who found that thing, but people have just done. Well, hang on, I'll show you something pretty cool. Hang on a second. All right, well, now, as I mentioned just a few moments ago, the glider gun thing, that gets to be quite important because people started thinking, well, it's interesting, but what use is this? What can we do with it? Well, then they started thinking about it. If you notice, this represents one of our glider guns. And here's a little glider, another glider. Every, what is I think, 5 cycles, 5 generations, another glider pumps out, another one pumps out, another pumps out. Now, that constant stream of gliders, you could think of that as a signal, like an electrical signal. At a certain timing, if there is a glider right here at a specific time, well, that's on, or true, or 1. Now, if here we have a situation, we've got, this is a glider gun, we'll call this our source, and here's an input. At the moment, we have no gliders coming. This is switched off, if you will. So nothing interferes with the source. It just keeps coming down here, and our output is 1. Okay, very cool. Well, that's good to know, but let's take a look at, all right, here we have the same situation. We've got our source here and our input. But look, if we send an input in here, what happens? Well, these gliders are coming down trying to get to the output. But if we have to turn this input on, these gliders come down and they collide and destroy each other. So we get nothing out of the output. If you remember the last image, we had 0 in and we got a 1 out. This time we put 1 in, we get a 0 out. This is a logic function known as NOT, because what comes out is not what goes in, or what goes in is not what comes out. Basically just inverts. If you put in a 1, you get out a 0. You put in a 0, you get out a 1. Simple as that. That's interesting, but can we do anything else with this? Let's take a look. All right, here we have what we call the AND function. Now, if you notice, our output is down here. We got input A and input B, and this is just a constant stream of gliders. I call it a disruptor. So at the moment we have 0 on the A, 0 on the B. They're both off, and we get nothing out. Let's try turning one of these on and see what we get. Now in this case, we've got our same situation. The 2 inputs here. In this case, input B is on, or 1. But again, nothing's coming to the out, so it's just nothing. Let's try another. Here we've got the same situation, except in this case, A is on, A is 1, B is 0. So we got a disruptor coming through here. Now these would go to the output,
But the disruptor comes along, collides with it, so it kills him. We got 0 out. Now, what else do we have? Well, one more possibility. Now, if we look, what A is on, so that's on, and B is on. And what's happening is A is the source that's coming down to the output, and it's getting through because B is also on, and it's stopping the disruptor. So if both are off, we get nothing out. If this one is on or that one is on, we get nothing out. Only when A and B are on, that's the only time we get an out. This function is known as an AND function, obviously because you need A and B. All right, let's keep thinking. What other kind of functions can we do? Well, let's try this one. Here we have what's known as an OR function. Our source is here, just pumping out the gliders coming toward the output, but the disruptor is coming along, and it, of course, disrupts the signal, so we get nothing out. If we notice A is off, B is off, so 0, 0. Well, let's see what happens here if we try something a little different. All right, in this case, we've got our source headed toward the output, and B is on, so it blocks the disruptor, and the signal gets through to the output. What else can we do here? Again, our source is trying to get to the output. In this case, A is on, so it disrupts, it collides with the disruptor and allows the signal to go through. And finally, here we've got our source pumping out the gliders. A is on, B is on, and it stops the disruptor so the signal goes through. So, if A is on, or B is on, or both are on, then we get a signal out. This is what's known as an OR function. Now there are electrical circuits that perform this exact function, and they're called logic gates. You've got NOT and an OR, which we just saw. And these can be combined in countless different ways. They have all kinds of different logic circuits, if you will. So what we have here are the beginnings of a computer. Could we actually simulate a computer in the game of life? Well, the fact that I'm asking the question should be an answer. Yes, of course you can. And if you can, people have. People have strung together a bunch of these, a bunch of different formations. You got all the glider guns, and of course there's also the horizontal spaceships. People spent way too much time in the pursuit, but they've actually created or simulated full computers in the game of life. And now what does a computer do? Well, a computer runs programs, right? People have actually programmed digital clocks, the digital displays in the game of life where you see ones and zeros and everything else, tic-tac-toe games, I think maybe checkers. And what's another program you might run? Well, what about the game of life itself? It's a program. So could you run the game of life in the game of life? Yeah, it can and has been done. And in fact, at least one person has run the game of life in the game of life in the game of life. So it's a simulation of a simulation of a simulation. I guess it's like simulception, whatever. Take a look at this. I think you'll get a kick out of it. Hang on one second. All right, if you notice here, what we've got, these are all little spaceships or gliders coming along here, and here's the glider guns over here, create more gliders. If we zoom out, what do we see? That's a live cell, another live cell. Bunch of dead cells. We zoom out, even more. This is from a video I found on YouTube. I will leave a link to it in the description so you can. It's an hour of this going out. There's beautiful music, but isn't that wild? This is a simulation of life. There's the spaceship about to go. Yeah, he's moving downward. And each of these spaceships, as you saw before, this is another live cell. There's the dead cell. It goes on and on. I mean, life within life within life, which just blows my mind. But as I say, people have run this on super duper computers with tens of thousands of columns and rows and millions of cells, as you see here. They've come up with just amazing things. There's entire branches of computer science based around the game of life. Chaos theory, what's another, I don't know, chaos theory and game theory. But it's pretty mind-blowing, I think. You can find this video and others like it on YouTube. Hang on a second here, pause this. Alrighty, here we go. Let's crack open this monstrosity of a program and see what makes her tick. Starting at the top, of course, QBA36.base, Life and Death, copy left once again, 2026 by Dr. Doodle. And as usual, we initialize our program first. Typically, our first command is def int, or default integer. Basically, this makes all our variables integer by default, just to speed the program up. Then we declare sub mouse func, and for those who haven't seen view subs mouse, this is the sub procedure that allows us to use the mouse in QBasic programs, and you just call it with a function 1, 2, or 3. 1 shows the mouse, 2 hides the mouse, and 3 reads where it is, what buttons are pressed. So back to the main program here. We declare our sub. Now we have 2 arrays with dim population 1 to 2000, and my life 1 to 2000. So the population, that's obviously the population. Basically, when the program scans the screen, it looks at every square and stores the status of each square in the array called population as 1 to 2000, because it's 40 by 50, 40 rows by 50 columns, which ends up to be in 2000. So 2000 cells total, and this stores the population of each one of these cells. My life is a separate array specifically for the cell that's being scanned. And we'll get to how that works later. But again, that's 1 to 2000 because there are 2000 cells. Restart. This is if we hit postmortem, we end our program, we want to start over again. We come back up to here. We reinitialize all our variables. X is set to 10, Y is the 10, size is the 10. Color 1 is 14, color 2 is 1, and color 3 is 9. Now, you can mess with those colors. Just make sure that 2 and 3 are not the same. You need a distinct grid there. If you can't see the grid, it doesn't draw properly. But you could, for example, have a red live cell, a red dead cell, whatever. You can play with the colors, do what you want. Index equals 0, alive equals 0, generation is 0, and active equals 0. Now we randomize the timer, so when we hit the random button, we'll get a genuinely random distribution of cells. We go sub do screen. Again, we've seen this many times. Do screen is a subroutine that just draws the screen, and we'll scroll down here, take a look at it quick. Subroutines do screen. We set to screen 12, which is 640 by 480 pixels and 16 colors. Turn the mouse off, clear the screen, and now we draw all the grid, the cells, if you will, the title box up here, then all the buttons, start and pause button, clear button, random, postmortem, help, and quit. So it just draws the screen, basically. All right, page back up here. So we go sub do screen. Now we do mouse loop until b equals 0. So if we actually held the mouse down, we just wait until you release the mouse and we can begin the program. Now we come to the main program loop, which is actually pretty simple. If active equals 1, then go sub start, which at the moment is not, but we'll see how that happens. Now we do mouse 3 to read where the mouse is, what buttons are pressed. And if B is greater than 0 and H is less than 501, then go sub populate. If B equals 1 and H is greater than 500, then we go here. And what we're doing, we're looking at 500 pixels over. If you're to the left of this, then you're in the grid and you go sub populate. This is what allows you to click on the particular cells and either turn them alive or dead. If you're past 500, then you're over here in the menu. And in this case, select case V, the vertical position. From this point to this point, we go sub activate, that's the start button. Down here is restart, then scramble. I really wanted to call that randomize, but of course randomize is one of the keywords, so you can't use that. So I call it scramble.
Below this, if you go down lower here, this is the post-mortem, then help, and finally quit. And select end if and loop. Then if you exit the loop, go sub quit the program. So we loop through here. We're looping until the end key is pressed, or you click on the quit subroutine. So we're looping through, and if you're less than 500 pixels to the right, then you're in the main, you're in the field, if you will. We call this populate subroutine. If it's more than that, then we go to the menu functions here, which we'll see. All right, we'll tackle this one by one here. So let's go to populate. And as always, the subroutines are doing all the hard work. Now we see do screen again. That sets the screen mode, turns off the mouse, draws our title boxes. We just took a look at that. Simple stuff. We've seen that many times. Now start. Excuse me. Well, first of all, I should do populate because that's mentioned first. All right, now populate. First thing we do is call mouse 2 to turn the mouse off so that it won't interfere with the graphics and leave the distortions and such. Now we call mouse 3 to read where the mouse is. And if H is less than 1 or H is 497, then return because we're out of bounds. Likewise, if V is less than 1 or V is greater than 397, then return. We're out of bounds. So just exit here. We're not doing anything. If we're in the field, then we select case B. Case 1, paint, H and V, color 1, and color 3. So in other words, if you happen to hit the left button, then wherever your mouse cursor happens to be, we paint that color 1 until it hits the grid, which is color 3. Case 2, if you have hit the right button, we paint color 2, which is either the black or dark blue in this case, whatever, and the grid is color 3. And select, then we turn the mouse back on and return. So all this does is looks where the mouse is. If you click the left button, wherever you are, it turns the cell yellow, live. And if you hit the right button, it turns it the background color, in this case a dark blue. Now that's it for populate. So go back up here. What's next here? Okay. Case 52 to 82 go sub activate. This is if you click on the start button, so we'll go down here to activate. Now, activate starts with a toggle. Active equals 1 minus active. So it starts out 0, and when you call the subroutine the first time, active is set to 1 minus 0. So it turns to 1. Next time you call it, it's 1, so it set equal to 1 minus 1 or 0. In other words, each time this line is called, it flips between 1 or 0, 1 or 0, 1 or 0. And this way we can start and we can pause, start, pause, that sort of thing. So mouse 2 turns off the cursor so it won't interfere with the graphics. We locate 5 and 70 up here, and if active is 1, then we print pause. So if it's actually working at the moment, if it's simulating, then this button should read pause. Else hit start because it's turned off at the moment, so we want to start it, so it should read start. End if. And then line, that just draws the line around the field. Do mouse 3, loop until B equals 0. So basically, until you release the mouse, it just waits for you to release the mouse. Turns the mouse back on and return. Simple enough. Now let's see what's down next. Okay, yeah, case 102 to 132 is restart. That's where we clear the screen and we go back up to the restart button, start all over again. We've cleared out the arrays, we've cleared out the screen, and we can draw more cells or we can randomize whatever we want to do. Next one down is scramble. That's the randomize function, so we'll go to the scramble subroutine here. Okay, scramble. When you hit scramble, it automatically activates, so active is set to 1. Line there to there, 0, and box fill. Yeah, and locate, print, pause. So then when you hit scramble, the start button is changed over to read pause, because when you click start, it will pause it. Either start, pause. Now we do mouse 3 and loop until B equals 0, until you release the mouse. Now mouse 2 turns off the mouse cursor. For B equals 1 to 40. For A is 1 to 50, and that's 40 rows by 50 columns. Now we've got Z equals random times 9 plus 1. This will give us a number from 0 to 10. Now if Z happens to be greater than 8, so if it's 9 or 10, then we paint A times size, B times size, color 1 and color 3. In other words, if the Z, the random number, happens to be greater than 8, so if it's 9 or 10, then it sets that cell to life. Next A, next B. And then again, we read the mouse, loop until the mouse equals, B equals 0, until we release the mouse. Then we turn the mouse cursor back on and return. Simple enough. Okay, back up here, and our next subroutine is postmortem. Now, postmortem will come down here. This is the subroutine we call when our field has gone stagnant, or if it's vacant altogether. Basically, it's dead, so you want to find out how many generations it took, what the population is, and the status of the thing. So, postmortem, first thing we set active to 0, so it stops what it's doing. We locate and print start, and turn the pause button back into start. Population equals 0. Excuse me, 0. Now, for y equals 1 to 40 times size, step size. In other words, it goes cell by cell, and then same with, y is vertical, x is horizontal. It's just going through cell by cell. And c equals point, x plus 5, y plus 5. Now, it's plus 5 because if you just do x, it'll be right on one of those grid lines. It'll be a dark gray or whatever color you set for it. You want it to be basically in the middle of each cell, so it's x plus 5, y plus 5, and we read the point that reads what color it is. C equals point. Now if C equals 14, that should actually be color 1 instead of 14. But in this case, if C equals 14, then pop equals pop plus 1. So it's reading every cell, and if a cell happens to be 14, oh, there's a live one, we add another one, there's another live one, there's another live one, and if. Next X, next Y. It just goes through all the cells, finds how many live ones there are, that becomes your population. Now select case pop. Scroll down here a bit. Case 0, status equals vacant. Again, if there's nothing alive, the whole universe is dead, is vacant. Case 1 to 200, status is stagnant, and it doesn't necessarily, you can actually hit postmortem before it dies, but at that point, with only 200 or less cells, it's pretty much going to be stagnant if it's not already. Case 201 to 1600, status is chaotic. It could keep going for, it may eventually static, but it could keep going on forever. And case else, if you got more than 1600 live cells, status is viral. At that point, it's probably just going to keep expanding. And again, these are kind of cheats. I don't really know how to tell mathematically whether, there's really no way to tell whether a particular situation is going to go stagnant or keep growing or go vacant. But this is just kind of a rough guidelines or a guesstimation, if you will. And it looks cool on screen, so I put it in there. Now this draws the little line around the box there. Locate here and print generation, population, using, I don't know if we've done it before, but if you haven't seen it before, using formats the print. So it'll print the population up to 4 digits. And instead of going 1, 2, 3, up to 9, then 10, 11, 12, up to 100, it starts from the right and works left. That's what using does. Yeah, you can, in fact, let's take a look at using, because it's a very helpful function. And let's see, print using. Yeah, it formats how it prints. Now here's the format specifiers. That's a digit position. You can just specify you want so many digits before the decimal, so many after. Place at the end of the decimal point, that prints a comma every 3rd digit. You can position of the number sign, prints an exponential format. We can prints trailing sign for numbers, leading dollars, all different. For string expressions, for numeric expressions, you can just format how it's printed. So this prints out the population, the generation, the status, and then we wait until we release the mouse and then return. What's next? Page up. Okay, next is the help screen. I'm sorry. Next down is the help button, the help subroutine, and this one's lengthy, but it's just basically artwork, really. No active statements. Well, it turns active off. Draws the line to clear the screen, then line, and here we, okay, here it's print still lives, and there's the block, there's the beehive, the tub, all these locate paints. Then we get to the boat, the aircraft carrier. Oh, here we go, print blink oscillators, draw the oscillators, the blinker, the toad, the beacon, all the different oscillators, the clock, the decathlon. Now we come to spaceships, where we draw the actual spaceships. All these paint functions here, they draw the glider. Down here we come to the lightweight spaceship. That's the one that goes horizontal. And by the way, being symmetrical, you can rotate, you can flip any pattern here, top to bottom, left to right, or rotate 90 degrees. It's all symmetrical, so you could have the glider going, or the spaceship going this way, go right, up or down. You can have a glider going direct, diagonal down, to the left, up, to the right, whatever. Any way you want to set it up. And again, it just paints the various, so you can get an idea how the different patterns you can put in there. Okay, next, that's the help subroutine, and finally quit. Quit's very simple. Come down here, quit. Mouse 2, clear screen system. Boom, just shuts the program down. Now there are a couple things we have not yet talked about, because these are subroutines that are called by other subroutines. For example, where was, I think, start? Yeah, start. These are this is where the nitty gets really gritty. Is the heavy lifting here. We go when we click the start button, we go scan, go update, and then generation equals generation plus 1. So let's take a look at scan. As I said, scan is where it actually looks at the field and see what's alive, what's dead. All right, this gets a little kinky here, but the math, we'll go through it step by step. For the scan subroutine, we start out setting the index equal to 0. Now for scan y equals 1 to 40, that's the 40 rows, and then scan x equals 1 to 50, that's the 50 columns, times size, the size of each cell, and the step size, so it goes one cell over each time. So it starts out with 1, 1, this is the first cell here, and box 1x, that's the horizontal of the first box, equals scan x plus 1 minus size. So if you're scanning, for example, this cell here, it subtracts size to go 1 to the left. Now box 1y equals scan y plus 1 minus size. The vertical subtracts size to go 1 up. So box 1 is whatever one you're scanning right now, it goes 1 to the left, 1 up, because we're subtracting size and we're subtracting size. Box 2 scan is equal scan x plus 1. Box 2y equals scan x plus 1 minus size. So box 2 scan is the same, it's right above the center, so we don't need to subtract or add anything in the size. But the vertical is on top of that cell, so we subtract size from the vertical, yeah. So the first time we're subtracting size to move one cell to the left, we're subtracting size on the vertical to move one cell up. Next time we're doing here. First time through, we subtract size on the horizontal to move over one cell, and we subtract size on the vertical to move up one cell. Now the next one is reading this cell just above there. We don't need to move over left or right, so we just subtract 1 from the vertical to move up 1. Next one, we're over here to the right, so when we scan this, we add 1 size to move over to the right, we subtract 1 size to go up in vertical. Next we come here and we subtract the size to move to the left. The vertical is good, we don't have to worry about that. This of course is box 5, that is our actual live cell. Next cell, we add 1 to the horizontal, so box scan x plus size. We don't have to worry about the vertical, it's already the right vertical position. Now here we subtract 1 size for the horizontal, we add 1 size to the vertical to get this corner. Next we come here to the box 8, we just add to the vertical, we don't have to add or subtract to the horizontal. And finally for the number 9 here, we add 1 to the horizontal, we add 1 to the vertical. This is how we scan the different cells. Okay. And here we see the scan x plus 1 minus size, plus size, minus size, plus size. Over here, minus size, plus size, minus size, plus size. So it's just going cell by cell. And box 5x, that's U basically, or whatever cell it's scanning. Box 5y is scan y plus 1. Now, we've got all this information. Hi, baby. Oh, careful, honey, that's hot. Gypsy just walked by the lamp there. No, that's hot, sweetheart. You're going to burn yourself. Yeah, it's bright too. You're going to blind yourself. Okay, so if scan x is less than 11, then that means if scan x is over to the left, then box 1x equals box 1x plus 50. Remember I said if you're over here to the right, it adds 50 to read this cell on the far right. So if box 1, the top left, if that's less than 11, then we add 50. Box 4 is immediately left of the cell. If that's less than 11, then we add 50. And box 7 in the bottom corner, if that's less than 11, we add 50 to read this cell on this size. And scan x equals 1. Okay. And if. Now, if scan x is greater than 49, then if it's over here to the right, then box 3x equals 2, box 6x equals 2. So in other words, it sets it back to 2. Scan x equals 49, and size equals size plus 1. So it just sets it. If it's on either side, then it scans the cell on the other side and sets the scan x to the proper position. Meanwhile, scan y, if scan y is less than 11, then we add 40 to bring it down. Same idea, it's just vertical instead of horizontal. If scan y is greater than 39, then they set it back to 2 up to the top, and we set the scan y to the correct location. Now, we've scanned all the 9 cells. We start by setting body count equal to 0. Box stat 1 equals point box 1 x box 1 y. If box stat 1 equals color 1, then body count equals body count plus 1. You can't see it over there, but body count equals body count plus 1. In other words, we create a variable. This is for the box 1, the top left corner, status. The point reads the color of that cell. So we look at box 1x, box 1x, box 1y, and if that happens to be the color 1, then it's alive. So body count equals body count plus 1. Now we go box 2, which is straight above the middle cell. And box 2 stat, if the color of box 2 is color 1, like in this case 14, it's alive, so we add 1 to body count. Same with this. It looks pretty complicated and everything, but it's all just repetition basically. We look at the given cell, the box 1 status equals point, the color of that box location. If the box happens to be the color 1, the live color, then body count equals body count plus 1. We go through the 9 boxes and we get our body count. Now, alive equals 0, and we're reading box 5 stat. Remember, that's the center. 1, 2, 3, 4, 5 is the center. That's the one we're currently scanning. Box 5 stat equals point. Box 5 x, box 5 y. If box 5 stat equals color 1, then I'm alive equals 1. So we start out setting just assuming it's dead. But if that cell happens to be the live color, then it's alive. So it's that I'm alive equals 1. Well, let's scroll over here. If box stat equals color 1, then I'm alive equals 1. In other words, if the center cell is color yellow, then in this case, whatever live color you choose, then I'm alive equals 1. Now, index equals index plus 1. And this is how we store that all into the variables, the arrays. Population index equals body count. So start with index 1, that's the first index in the array, and the body count, how many cells are alive around that first cell. That's the population. My life is that particular cell, is that cell alive? Next scan X, next scan Y, index equals 0, and then return. So what this does, it goes and scans every cell, all the 8 cells surrounding every cell, and looks at the colors of those cells. If each of those cells is alive, well, if box 5 is alive, then I'm alive equals 1. Any of the surrounding ones, if they're alive, we add 1 to the body count. This is how we know there's 0 live neighbors, or 1 live neighbor, 2 live neighbors, that sort of thing. Now we've scanned all this information, stored it into the population array. We know where the live cells are, where the dead ones are. Now we need to apply the rules of the simulation to each cell, so the next generation will reflect what dies, what comes back to life, and what survives. So we go to subroutine update. Mouse 2 turns off the mouse cursor so it won't interfere with the graphics. Index is 1, so we start at the beginning of each array here. For scan Y is 1 to 40, scan X is 1 to 50. We're just going through scanning each cell. And color is set to color 2, the dead color, whatever color you happen to be. In this case, it's the dark blue, but we just assume that the cell is dead to begin with. Now we select case population index. And the population will show the body count. It will show how many live neighbors there are. So in case 2, if my live index equals 1, if this cell is alive and it has 2 live neighbors, then color equals color 1. Now if it happens to be dead, then it will just stay dead. But if case 3, if it has 3 live neighbors, the color equals set to color 1. So whether it's live or it's dead, it comes back to life. And I'm not sure if I explained that quite well, but it reads the index for population, and that has the body count. That's how many live neighbors there are. In the case of 2 live neighbors, if the cell is already alive, then it stays alive. If it's dead, it stays dead. Now, in the case of 3 live neighbors, color is just set to color 1, the live cell, because even if it's alive, it will come back to life. And select. Now we paint that the relevant cell, we paint it the color. It's either color 1 or color 2. And then color 3, that's the border. So it paints whatever color and to the border. So it checks how many neighbors there are and puts it either to live color or dead color and paints it. Now index equals index plus 1, scan X, Y, next scan Y. So it just goes through cell by cell by cell. When it's done, it turns the mouse back on and returns. So if I can explain this more properly, turns the mouse cursor off so it won't interfere with the graphics. We set index to 1, so we're starting the first cell. We scan X to Y, that's just our loops. Color is set to color 2, which is the dead color. We just assume they're dead to begin with. Now we select case population at that index, whether it's the first cell, second cell, third cell. If the body count, if there's 2 neighbors and this cell is already alive, then color equals color 1. If it's dead, then it stays dead. If the body count is 3, if there's 3 live neighbors, then either way, color is set to color 1. Now we've got the right color. We paint that cell color 1 or color 2. Actually, we won't have to paint it if it's already dead. But it paints the color, and then index equals index plus 1. We go to the next scan. The next scan just loops around, and it updates each cell one by one by one. Boom, that's the update function. So that's the code. As dense as it is, it's pretty intense, but if you look through it a couple times, download the code and look through it, and hopefully it should make sense to you. But most of the draw screens, the help, they just draw the graphics on screen. Necessary graphic. Now scan and update, those are the 2 main subroutines. They do the actual work. Scan scans each cell and the 8 cells around it, so it sees, is this cell alive? How many live neighbors does it have? Once it has that information, it looks at the body count, and it adds the here, if this neighbor and this neighbor and this neighbor are alive, the rest are dead, then the body count is 1, 2, 3, etc. So it calculates the body count, how many live neighbors you have, and then stores the information into the population index. So the population at that position is the body count. How many live neighbors there are. Population at this location, whatever the body count is, it stores the information about how many live neighbors each cell has. I guess that's the best way I can put it. Also, my life index, I'm alive, it stores information whether the main cell is alive or dead. So that's how we know where everything is and what we need to do. Now, update applies those rules. It goes through cell by cell, starts out assuming that they're all dead. Now it checks how many neighbors there are. If there are 2 neighbors and the cell is still alive, then it stays alive. If it's dead, then it just stays dead. If there are 3 neighbors and the cell is dead, it comes back to life. Then it paints the appropriate color. Index equals index next plus 1 to check the next cell, and then next X, next Y, turn the mouse back on and return. I don't mind telling you, it took me a while to figure this out, but the basic idea, it just looks at the cell by cell, it scans, is this cell alive? How many live neighbors are there? Stores that information into a couple of arrays. The population array, that's how many neighbors there are, and my life array is whether that cell is alive. Once we got that information, we go to update, which reads the information and says, oh, there's 2 neighbors or there's 3 neighbors, and then it paints the cell the appropriate color, whether it's live or dead, and just goes cell by cell by cell. That's all there is to it. Lather, rinse, repeat. Just keep looping until someone clicks on quit. Then mouse 2 turns off the mouse cursor, clear the screen, and system. Oh, that's the end of it. I hope you're less confused than I am, but this step by step, that's the way it works. And it's time to take a look at Supeeriors. Oh, this is the great Supeeriors. All right, so that pretty much covers our code. Now it's time to zip on over to Supeeriors. Got a great one this time. Great. This one, this is the YouTube channel called mathandscience.com. Yeah, mathandscience.com. Our host, Jason Gibson. Guy's a smart fella. Let me tell you, a hell of a teacher. He can explain it. I'll let you see for yourself. Hang on. Supeeriors. All right, guys. Well, here we are at the YouTube channel of mathandscience.com, where our host Jason Gibson here, brilliant fella, he helps to explain topics such as algebra, calculus, physics, chemistry, statistics, engineering, and more. And I tell you, I am, you know me, I'm tripping over my words left and right, but this man, he can just make any topic let's just take a look at the first one here. What says binary explained. Everything digital is just zeros and ones.
Hello, welcome back. I'm Jason. I want you to think back to those old vinyl records that would spin on the turntable. So the music you hear way back when using that analog format was really from tiny physical grooves, little microscopic mountains that are on the surface of the record, mountains and valleys, and as the needle traces over, it follows up and down like a roller coaster. So as the stylus
All right, well, as we all know with records, they are an analog representation of sound. It's literally in real time. It carves out the waves and the shapes of the sound that's being recorded. But of course now in digital we've got to sample that somehow, turn it into binary ones and zeros, digital, and he goes on to explain how that's all done, which really cleared up a lot of things for me. What's next up here? Okay, if we can't see atoms, how do we know what's inside? Well, let's see what he has to say.
Now, it's absolutely crazy to me that everything you've ever touched, everything you've ever eaten in your whole life, everything you've ever breathed into your body, everything that you have ever come into contact with in your whole life, every single bit of it is actually made of atoms that you will never directly see. And inside those tiny atoms that you've never seen with your own eyes are electrons that you've never actually seen, or protons and neutrons that you've never actually seen. So here's the wild question for today. How do we actually know what's inside of an atom, what the inside looks like, or what's actually inside of something smaller than you've ever actually seen with your own eyes
Someone's
or
come to
directly
visit.
observed? In other words, if we can't actually
girl.
see
What are you doing,
individual
little baby?
atoms, how do we actually know what they're really made of?
Oh, that looks cool. All the superconductors, magnetism, that's fun. Yeah, I've seen those fire pistons, they're cool. The marshmallow, that's neat. Yeah, so in the case, like he says, how do we know what's inside the atoms? Well, just watch the video and he'll explain it to us. Let's see what else is up here. Oh, if a laser is just light, how can it cut through metal? Gypsy baby, hi honey. Hang on a second. My little girl is, hi honey. You want some attention? Hang on 1 second, little one. Here we go.
Now, you've probably seen videos of lasers slicing through metal like butter. Or you might have wondered why you've been warned never, ever, ever to point a laser pointer or any laser at an airplane. But here's the wild thing. Laser light and the light from your phone or any other light source are made of the same exact stuff, photons. Yet, a laser can somehow cut through steel, and the light from a phone can't even warm your face. So the question then is...
Oh, careful, honey. Little goofball. Anyway, yeah, so if a laser's just light, how can it cut through metal? I watched this earlier, and he goes on to talk about energy density and how... Oh, silly girl, what are you doing? Oh, this crazy cat. Get off of there, Goofy. Come on out. Oh, down you go, baby. Good girl. Hang on 1 second. There we go.
Is what makes a laser so special, and how exactly can lasers
Everybody's
and laser
a critic.
light
Hang on.
burn
All
through?
right, let's continue here. Now that we got Gypsy, I thought we had her out of the way, but no, those are my headphones. All right, you have the headphones, if it keeps you happy. Yeah, here. The little twerp, there she is with my headphones. What am I going to do with this cat? Anyway, I love her. So, let's go on to the next video here. What do we got? Gypsy, come on. Girl, no, don't eat the cords. Look, come over here. Over here. Over here. Yeah, you play with that. All right. Learn, practice, and master the rules of exponents in algebra. Oh, I know math, but here we go.
Your phone just took a photo. But in the time it took you to do that, a virus on your device, if left unchecked, could actually have replicated itself into the billions. Not the thousands, not the millions. I'm talking about the billions. Now, this is actually not science fiction. That's exponents and exponential growth. We live in a world that doesn't really grow in straight lines like you learn in algebra class. It doesn't really add constantly. In many cases, it multiplies. Now, the mathematical language behind that multiplication that we see in everyday life, in other words, the tool that lets the scientists, the engineers, the economists, the doctors, and so on, the tools that actually work with those numbers is actually called the laws of exponents. Now here's what this means in the simplest level. When something doubles repeatedly, like think about a population of bacteria doubling over time, or an investment growing in your bank account, it could be a signal bouncing through a fiber optic cable, for instance. The numbers in those situations get astronomically large, almost instantly, because of exponential growth. And without a structured way to write down this kind of growth, or to simplify expressions with exponents, or manipulate those kinds of numbers, the math becomes completely unworkable. In other words, exponent laws are the rules that make it workable.
Yeah, I know math, but I mean the channel is called Math and Science, and yeah, knowing about exponents, trigonometry, algebra has come in handy quite a bit for me in my programming, and other fields of life. I'm sure it comes in handy, so that's a good one. And he really does lay out how exponents work quite well. That's what we got next here. The last one we'll check out here: the deepest point in the ocean and what we found there. Oh, that's cool. What's this all about?
I want you to imagine descending into absolute darkness, going deeper than Mount Everest is tall, until you reach a place deep down where the pressure would crush an entire car like a can of soda in just milliseconds. Now we're talking about going underwater, way, way deep underwater, where the water here weighs down on you with a force of over 1,000 atmospheres. Now
Holy
that's
crap.
kind of like having 50 jumbo jets stacked on top of each other for every square meter pushing on your body.
Oh, I'll pass
This
on that.
is
Thank
the
you very
Mariana
much.
Trench, the deepest place
Wow.
on Earth, and until very recently, more people have actually walked on the moon than had been to the bottom of this place on Earth.
Wow, that's
But
pretty
we've
amazing.
been down there now, and what we found actually challenges everything we thought we knew about where life can exist on this planet. So even at these
Look at that.
crushing depths below the surface of the water, this isn't some lifeless void. It's an alien world teeming with creatures that shouldn't be able to survive based on common sense, thriving in conditions
Oh, wow,
that
it
would
glows in the
actually
dark.
kill us instantly. So today I'd like to take a deep dive, literally, into the deepest, the darkest, the most mysterious place on our entire planet. Today we're going to go to the bottom of the Mariana Trench.
All right, well, if you want to see what they find there, you just have to watch the video, the deepest point in the ocean, what we found there. Oh yeah, I'm telling you, this channel has got, what have we got here? Almost 4,500 videos, so there's something for everybody here. Again, algebra, calculus, physics, statistics, engineering, even chemistry. You want to know something? I'll tell you, come right here, you will find it out. And Jason, Mr. Gibson, he does a great job explaining everything. Well, you heard him, how clear and concise he is, and wow, he can make any topic interesting and intelligible. And you've got to check out mathandscience.com. You will not be disappointed. It's a great channel. I've been here many times and seen lots of different great videos. So check it out, and yeah, you'll be glad you did. All right, that's it for the Supeeriors. Now it's time to head on back to the video, wrap this piglet up, and let's get you out of here. Hang on a second. So there we have it, gang. We've covered our code. We've seen what the program does, and yeah, this one is just such a milestone in computing and kind of a personal rite of passage for me. I've been wanting to get one of these, a version of this, for a while now, and I'm pretty happy with what I've come up with here. But yeah, so we've seen the program. We went to Supeeriors, and again, mathandscience.com. You got to check out that channel. You will be. You'll be so glad you did. Jason, hey, thanks for your hard work there on mathandscience.com. Check it out, gang. I guess all that's left to say is thank you so much for watching. I hope you enjoyed the program. Remember to download the code, mess with it, and again, there'll be links to the videos and such. And well, just enjoy it, have a good time. Thanks again so much for watching, and I hope to see you again next time. And until then, as always, hasta la pizza, baby. You know, just one more time. Let's run this pig just for one more time. Hang on. All right, let's take one more whack at this puppy and see what we end up with. We'll just randomize here.